Okay, speak.
Hello? Hello?
Good.
So I think she was trying to turn it up and up and up as I spoke, and then...
It was muted, so when we tried to turn up the volume,
Got it. Okay, sorry that I didn't notice. So, yes, we would like a language for describing pulse schedules for which formal semantics are possible, so that we can have a verified compiler that outputs them. And here are at least the first steps, we say in this direction. We come up with the name Grampus, a graded modal type theory for pulse schedules. Graded modal is a fancy name for a relatively simple idea. We annotate every variable with a grade or a modality, in this case denoting the moment in time. So negative numbers denote moments in the past, positive numbers denote times in the future. As a simple example to start with, assume we're compiling this quantum circuit on 2 qubits, 1 and 2, and we happen to know with the native gates on this particular quantum chip, Hadamard gate on the qubit 1 takes we know a pulse that implements the Hadamard gate that takes 110 nanoseconds to run, a pulse on the second gate that takes 100 nanoseconds, and the 2 qubit gate takes 500 nanoseconds on both qubits, of course. Then here is a pulse schedule or a program. If you give me a state of qubit 1 that existed 610 nanoseconds in the past, and a state of qubit 2 that existed 600 nanoseconds in the past, then I can give you a state of qubit 1 tensor product qubit 2 that exists now. The types that exist in this language, we have a unit type, we have a label for each qubit in the chip that we are writing pulse schedules for. You can put in tensor products, and we also have a type box DA, which internalizes the grades attached to the variables. So a value of type box DA, if D is positive, represents a value of type A that will exist D nanoseconds in the future. If D is negative, it represents a value of type A that will exist, well, negative D nanoseconds in the past. We can easily produce 2 versions of the language. For those of you, if the colors are visible, then we have the full language, which we call the annotated language, includes these grades for representing the times. And if you put on blue colored glasses, or just take away everything that is colored blue on the screen, we have what we call the plain language, which represents everything with timing information removed, and which is essentially the same as the language of quantum circuits, which is well defined with semantics that are well understood. I will show a very few of the typing rules. So if I know, given inputs gamma, how to produce a value of type A, then if I have inputs gamma D nanoseconds in the future, I know how to produce an input value of type A D nanoseconds in the future. If I know how to produce a value of A D in the future, and from a value of A that exists E in the future, I could produce a B, well then if you give me these inputs shifted by E minus D, I could give you a B. We can also apply quantum gates, and you can always just do nothing to a qubit for D nanoseconds. Those are the primitives. The plan for how this all fits together. So we have the annotated language, which has timing information, represents pulse schedules. The plain language, which is quantum circuits. The language before we have any timing information. You can always remove the timing information from a pulse schedule to get a quantum circuit. We know how to interpret a quantum circuit as a unitary in Hilbert spaces. We can compile from the post schedule language to the actual inputs that are sent down the input channels to the hardware itself. A hardware model should predict what any given input schedule implements, and so if we have done everything right, then this diagram should commute. The inputs that you get from a post schedule should implement the unitary from the associated quantum circuit. This should ideally be a diagram representing 4 homomorphisms between 4 models of our languages. And Lorenzo will explain what we mean by that.
Right. So I intend to start talking about the plain language. Most of what I'm going to say for the plain language will also apply to the...
I think your microphone is off too.
I put it on. Turn it on. Is it on now? Is it working now? Test? Yes. Seems to be working now. Okay. So everything I'm going to say, almost everything I'm going to say about the plain language will also apply to the annotated one. So, as we all know, quantum circuits can be interpreted as unitaries in the category of finite dimensional Hilbert spaces. The key aspect here is that Hilbert spaces form a symmetric monoidal category. The way we interpret types and contexts is relatively straightforward. Unit type is just the complex numbers. A qubit is going to be, well, the two-dimensional complex plane. Tensor product of types is going to be the tensor product of the corresponding Hilbert spaces. And we do essentially the same thing for contexts. For typing judgments, we do roughly what you would expect. I just present the example of what happens for a gate. So assuming we have derivations for all the terms that we want, you can think of n being either 1 or 2 for 1 and 2 qubit gates. We wanted to present this in a general way. And the way we do it is if context gamma I allows me to deduce ti, then I can just combine them by doing a tensor product and then compose them to, with the unitary that represents the gate. We do essentially the same thing for equality judgments. Of course, the interpretations are going to be built inductively on the, well, typing derivation. An example of the circuit we presented earlier, we interpret first the C naught to the corresponding unitary, and then we interpret the previous stages. We end up with identities, which we can just remove because composing with an identity does nothing. More generally, we can build semantics for the plain language for any symmetric monoidal categories, provided we make some choices. We'd have to decide which objects are going to be assigned to every qubit and which morphisms to assign to every gate. Of course, things have to type check, and then we do essentially the same thing we did for Hilbert spaces. Same example, but now we are using these more abstract symbols. It's essentially the same thing. For what concerns the annotated language, we can roughly do exactly the same thing. The only exception is for gates, because now gates will carry timing annotations. So we have an intended model in mind, which is the one of, well, channels and signals. And the way this works is we construct a category which has objects, sequences of qubits, each one annotated with the time. And then the morphisms are just going to be sequences of electrical signals to be sent to the machines. So for example, here we have a signal that starts 600 nanoseconds in the past and ends now, and another one that starts 610 nanoseconds in the past and ends now. We can generalize this as we did for the plain language. The extra structure we need on our symmetric monoidal category is that of what's called an R module category. So you can think of this as a symmetric monoidal category together with an action of the real numbers under addition. And we want this action to be monoidal so that shifting a tensor product is the same as tensoring the two types shifted separately. Again, the example of the gate rule. It's the same as what we did before, but now we have to shift everything by d, where d is, of course, the time it takes to perform the gate we are talking about. Everything goes through inductively in exactly the same way, and things work out for equality judgments as well. It turns out that we can prove quite a few interesting and expected properties. We can prove soundness and completeness. We can construct models from the syntax of each of those languages. And from this, I'm pretty sure we can also deduce normalization, even though we don't list it here. If the hardware model is correct in the appropriate sense, then the diagram that we showed earlier just commutes. So, in conclusion, we defined languages that can describe pulse schedules and can also describe scheduling strategies. So that, for example, deciding to schedule something as soon as possible or as late as possible or some mixed choice are going to be different, at least syntactically different. We are working on building a verified quantum compiler, which is on the URL shown here. The next step that we want to think about is how to add measurement for this. Because once we can add measurement, we will most likely be able to have full classical control, almost out of the box. This whole talk has been inspired by it's based on a preprint that we have on the archive. That's the link. Credit to how we found the name, we used acronymify online. So if it sounded weird, that's the reason. And yeah, that's it.
Thank you. Questions?
Thanks. Thank you for your talk. That's really cool. So one thing that I noticed from the types is that it seems to be assuming that you can always do nothing to a qubit. You can extend it into the future. Have you had thoughts about how to capture the idea that doing nothing to a qubit is, can affect the semantics, cause decoherence and things like that?
That's the problem, of course. You could just leave a qubit alone, then this would not be a difficult problem. The different schedule strategies would all do exactly the same thing.
But that's the reason why we have this delay operation here. This is not the identity, not at least by definition. When we erase, it becomes the identity, unless we extend the unannotated language with fake gates, which represent those delays. And that also just works because we didn't make any assumptions on the gates. So we can have an infinite family of delays for each qubit, if that makes sense.
So delay is some morphism from the qubit now to the qubit d in the future, not necessarily the identity.
So does the soundness property that you described in terms of this commutativity, that doesn't account for those delays though, right? Because in the erased program, it's just doing nothing.
Oh, I see. Yes, this is on the ideal quantum computer.
Yeah.
Yes, in this
Yeah.
model, yeah.
Yeah.
That's what we're talking about. Yes, if you include noise in your hardware model, then you're talking about how closely it approximates the target unit instead.
Thank you very much.
I think we have time for one more quick question.
Hi, thanks for the talk. I found it really understandable. You had so I think on the last slide you said that the graded modal language is, yeah, you said it describes pulse schedules. I was wondering how tight this correspondence is. So from every term of your language, you can get a pulse schedule. Is every correct pulse schedule, does it have a definition in your language, and is it one-to-one? And yeah, does that make sense?
Every pulse schedule can be represented in the language, straightforwardly. It is not, well, it's what it should be one.
Well, everything that's been built by the signals that you know represent a given gate. And every one of those corresponds to a program language.
Yes.
The ones that are built in a different way.
Sure.
Is it one-to-one up to definitional equality? Not necessarily. No, that doesn't follow just from completeness. I think it should be, assuming that there are no equations between native gates. Like if by coincidence the native gate correct sort of outcomes the same as some of the native gates. Good question. I think it should be, yes.
Thank you.